Let us use the Gauss-Jordan elimination in solving for this linear system, or specifically the values of A, B, and C. We are going to check whether there are infinitely many solutions, no solution, or there's our exact values for these mentioned variables. But this set of linear system, or this linear system rather, was already presented on a separate video in our channel. But in that video, we just ended up with the row echelon form, for the task was the Gaussian elimination. And since here we are going to come up with the Gaussian elimination, and Gaussian elimination is part of it, we are going to add the backward phase for the resulting row echelon form of the previous video. So let's use that. I won't be sharing the process of coming up with the row echelon form for the equivalent matrix of augmented matrix of this linear system. You might want to check that previous video, but I'm just going to present immediately the row echelon form after the application of the Gaussian elimination. So that was 1, 2, negative 1, negative 2/3, okay? 0, 1, negative 3/2, and negative 1/2, and I have 0, 0, 0, and 6. This was the row echelon form of this linear system after applying the Gaussian elimination. Now we are going to do the additional requirement, the backward phase, for it to be called Gaussian elimination. In short, from this row echelon form, let us come up with the reduced row echelon form, applying correct row operations as well. But before we go to that, it might be noted that with this given row echelon form, we have decided from last time that this linear system doesn't have any solution. It was indicated by the relationship of this third row here. The purpose of sharing this is that even if we are going to use the Gaussian elimination or continue this to come up with a reduced row echelon form, the solution should be the same. Okay, so if the Gauss-Jordan, if the row echelon form from last time after the Gaussian elimination showed that there was no solution, if we are going to come up with a reduced row echelon form for this after applying the remaining steps for the Gaussian elimination, it should also return to no solution. Because if they are not equivalent, that would mean that it's either the first part, the process of getting the row echelon form was incorrect, or probably the second part or the application of the backward phase for the Gaussian elimination might be incorrect. So our task here is to make this row echelon form into a reduced row echelon form, and we only have one additional concern. Let's make this 0, because this has met the 3 conditions, and the last condition for it to be called a reduced row echelon form is that for the same column having a leading one, all entries must be 0, meaning these 2 again, we will make that to 0, and we are going to apply this operation. We multiply negative 2 to row 2 and add it to row 1 to have a new row 1. Okay, so with that we'll have this. It's still 0, 0, 0, 6. You see, the conflicting statement of the third row is still present for the reduced row echelon form, but let's continue this anyway. 0, 1, negative 3/2, negative 1/2. So negative 2 times 0 is 0 plus 1, 1. Negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times 3/2, or negative 3/2, is positive 3. Okay? Positive 3. Plus 1 is positive 2. Negative 2 times negative 1/2 is positive 1. Plus 2/3 is positive 1/3. So this is now the reduced row echelon form of the augmented matrix of this linear system. And let's have its equation. So you have A as your first By the way, again, if you're wondering why there's one here where there's no a coefficient, there was a process of interchanging rows presented in the previous video for Gaussian elimination. Please check that one out. But in our equation here, it will present as 1 or a plus c is equal to 1/3. Now this might look very possible. Yes. Sorry, not c. It's plus 2c. That's very bad. And for the second row, we have b minus 3 half c is equal to negative 1/2. Might also be possible if we're going to allow one of the variables, say c, as arbitrary variable. But again, here comes the conflicting idea. 0a is 0, 0b is 0, 0c is 0, so the entire row is 0 and it's equal to 6. Of course, this is again not possible. This will return to the same decision that this linear system has no solution, just like the result in our Gaussian elimination in the previous video. So, as mentioned, the result or the solution for the linear system, whether it's under Gaussian elimination or Gaussian elimination, you will end up with the same result. For in this case, end up with no solutions. So if you are tasked to solve linear systems later and you are not limited to use a specific method, it's up to you whether you will use Gaussian elimination or Gaussian elimination. You're already assured of that the results are just the same. Thank you for watching.